I welcome you all again to this another session of physics classes. I'm Dr. Sumit Bhatnagar. I'm a faculty at Prepaze. Today we'll be doing on working on the work, power, and energy concepts. We'll be studying that. I would like to introduce you to Prepaze. So Prepaze is an online platform where you can get knowledge, help clarify your doubts at the comfort of your home. We have a team of very good experts in different subjects. So, whichever subjects you are having difficulty or you want any help regarding that, you can contact Prepaze and you can book a free trial class to see whether that teacher meet your expectations. All right, do check the website and book a trial class. All right, so let's start today's topic. So today we'll be doing work, energy, and power. Very important topic. So in mechanics, obviously, this all topics are extremely important. This is also one of the important topic and holds a good percentage of marks in exam in whichever exams you are sitting and preparing for. This is like one of the commonly asked topics in exams. So first of all, we'll be doing work. Now, what is work? Now, work done is basically work done by a force is the product of force in the direction of displacement. So product of force and displacement. So force is in the direction of the displacement. So that is basically the work definition. What is the formula, mathematical formula work done by a force? It is F into D into cos theta. D you can represent something like S also. Okay, some people represent by S to represent the displacement. Okay, or X or Y, whatever it is, but it is a distance or measured basically from the point of origin. So that is basically distance, or sorry, not distance, basically the displacement, because distance basically the force is basically we are involving. Okay, the force is a vector quantity, so we are taking a displacement. Sorry, not the distance, it is basically the displacement which we are talking about over here. All right, so just to make sure clarify that over here, I will just write S only to represent the displacement. All right. So this is basically how the work done is right. Now, what is theta over here? Theta is the angle. So theta is basically the angle between F and S. Theta is the angle between F and S. I told you from the definition, the force has to be in the direction of displacement. Suppose, let's say, consider a very simple example. There is a box which is kept on a smooth surface. There is no friction. There is a force which is acting on it, like if F in this direction. And the angle basically is this is theta, and this box is moving along the horizontal direction over here. It moves a displacement D, suppose, and F is acting like this. F is constant and acting as same angle theta throughout the displacement. Now, the work done formula by this force is what? I told you it is F into the displacement, which is D into cos theta. That is the formula. Now, why we are taking cos theta? See, if you are comfortable with vectors, what I just did make a component of this F. So this F is basically, this component is what? F cos theta. The vertical one is what? F sin theta. We're not taking the vertical component. We are taking the horizontal component of that, because the force has to be in the direction of the displacement. That is how the work is defined in physics. So let's say you are standing, okay, and there's a heavy weight, you keep it on your head. So you're just standing. So is there any work done according to physics by you? No. Even if you move, right? Even if you move horizontally, keeping that weight on yourself, is there any work done? No. Why? Because the weight is on your head. So mg of that weight will be downwards. You are moving it forward. So what is this angle? This is 90 degree. What is cos 90? It is 0. According to physics, there is no work done. Okay, but obviously there is work done. But that is a different aspect of that. We are not going in that detail. Right now, according to physics, what we are doing is basically this is the concept which we will be using for the questions we'll be solving. All right, this is basically how we. Now, another thing over here is that I would say it's analogous to that work only. We have energy. Energy is the rate, is basically the rate probability to do work. Probability, or better word will be ability to do work. So it is basically the ability to do work. The more the energy you have, more work you can do, right? Isn't it? So in the morning you are more energetic, obviously you can do more work. So you have, we say that you have more energy, that's why you are doing more work. So that is how energy and work are related. Both are basically same. Looking at the point of view, both are same, but how we define them is a different aspect. But actually they are same thing. What is work? It is, and we know that the SI unit of work is what? It is joules only, and SI unit of energy is also joules. There are different kinds of energy. That's mechanical energy, where we have electrical energy, we have magnetic energy, we have electrostatic, we have electrogravitation energy, thermal energy. All are different kinds of energy we have. Okay. Right now, for this topic, since we are relating to mechanics, right? we will be discussing the mechanical energy, your electrical energy, thermal energy, and your magnetization energy. All those things will be discussed in further chapters when I will be doing that. So I will introduce those energies at that time. Right now, let us just focus on the mechanical energy. Now, what is mechanical energy? Mechanical energy is basically the sum of kinetic energy of body and its potential energy. This is basically the mechanical energy. Both the kinetic energy and the potential energy are taken together. That is called the mechanical energy, and it is most widely used in physics. There are a lot of questions asked on this. So this is the mechanical energy. For example, how do you define it? Different kinds of mechanical energy. The kinetic energy of the body is basically due to mu, due to movement, basically the speed, velocity. So if the particle or a body have a speed or a velocity, we say it has a kinetic energy. All right. Now, why the potential energy is coming to picture? Potential energy is due to height, or mostly we say deformation, or we say height of the body. Or let us say that a body is at a height h, we say it has a potential energy, right? I will define what are the formulas of this. And suppose if I say that the body, suppose let's say a plastic ball, you squeeze it. Okay, what you're doing, you are changing its shape, and because of squeezing it, it's get deformed. There is a deformation. Or a rubber band, you extend a rubber band, you extending the rubber band, that is, you're deforming the rubber band. So in that process, basically what is happening now, there is a potential energy stored in the body. All right, and that's how we basically define potential energy. It can be due to change in shape, size, deformation, or due to the height of the body. All right, let's move forward. So the kinetic energy I told is basically what, due to the velocity of the body. So the kinetic energy is basically given by the formula half mv square. All right. There is another term which is change in kinetic energy, delta K. Is just that Ke final. We'll be using it, so you will understand it much better later on. It is this. So this is a Kf final minus Ki initial. So this is the idea over here. So it is basically half m. We can take common. It is Vf square minus Pi square. That's it. All right. That is how we define the kinetic energy. Now, after this, basically what we have is a potential energy. I told you, right? This, the most commonly used potential energy is one of this, the gravitational potential energy, right? Let's discuss that first. It's a gravitational potential energy. Now, what is gravitational potential energy? The formula is mgh. How we define it? Suppose, let's say, there is a body on the surface of the ground. Now, this body, it is taken to a height h from the ground. When it is a height h, it has a gravitational potential energy of mgh. When it is at ground, the gravitational potential energy is 0. Now, one concept I want to explain you over here. Whenever we are defining the gravitational potential energy, this concept will be mostly more discussed in detail in a gravitation chapter. The concept is basically that whenever we are defining the gravitational potential energy, we have to give a reference point. Always, by default, the reference point is a ground. Okay, normally it is basically from the ground to the surface only. It is ground. There we take the gravitational potential energy 0. Now, if the gravitational potential energy reference point at the ground is 0, then we can say that the gravitational potential energy at a height is mgh. That is how we define that. Potential energy, which is most commonly used, we'll be discussing over here. It is elastic potential energy. Elastic potential energy. Now, what is it? It is basically due to the stretch in springs or ropes. So these kind of system where you have a basically rubber bands, where you are stretching it, that is from the normal position, you are basically either compressing that thing or you are extending that thing. Both in the process, there will be an elastic potential energy stored. Very common example is of the spring. Suppose the spring is right now kept in its initial position. This is basically the normal length of spring, or normal position of spring. All right. Now, from this normal position, if suppose let's say you are stretching it by distance x, so you are stretching it now. Okay, it's called a stretch position. Or either you are compressing it from its normal position by amount x only, like this. It is called the compressed position. In both stretch and compressed position, there is an elastic potential energy stored in the spring. The magnitude of it is given by half kx square. X is the compression or the extension. K is called the spring constant. Spring constant. Unit is what we have of the spring constant is Newton per meter. That is how we define the elastic potential energy in this. So this was about these two energies we have over here. So the next thing which comes in this topic is the conservation of energy. This is called the law of conservation of energy. It is extremely important. Let us discuss that. What is it? So we have a law of conservation of energy, and the law of conservation of energy says that energy cannot be created nor destroyed. It can only be transformed from one form to another form. That is basically is the statement of law of conservation of energy. You cannot create it nor you can destroy it. You can just transform. Very good example I will tell you over here, where we are using law of conservation of energy. Suppose let's say there is a ball which is kept on the ground. Initially, you throw it upward with the velocity u. It will go up to its maximum height, let's say over here, h. Clear? We say if it is a maximum height, that what is the velocity over here? It is 0. Good, because it is a max height. Now I want, so suppose let's say this is a point A, this is a point B over here. I want to apply law of conservation of energy between A and B. It is always applicable. There are few like variations in this. We'll be discussing a few questions. So we say that according to law of conservation of energy, the energy at the point A of the ball will be equal to the energy at point B of the ball. What is the energy at the point A? Now, see, I told you at the point A, it has a velocity. So it will definitely have half m u square. That is a kinetic energy. I told you that the gravitational potential energy at the ground is we are defining by default as 0. So there is no gravitational potential energy. It is 0. What is the energy at B? It is kinetic energy is what? 0, because velocity is 0. So it is basically 0. What is the gravitational potential energy? It's mgh. So that means you got u square is equals to gh. 2gh, u is what? Under root of 2gh. That is the velocity basically with which the ball is thrown. Same idea basically you can use from kinematics. Kinematics also you can look at the same answer. That is obviously you can just use it and apply it and check it. Obviously you get the same answer. Suppose you want to find out the velocity at the height, what velocity you should throw. So this answer you'll get it. You can check it easily. But the idea over here is the explanation of that. What is the conservation of energy? How we can use that. I guess this session we are done now for today. Next session I will continue and I will give you more examples where law of conservation of energy will be used, and we will be proceeding with doing more complex question on that. So that's it. That's it for today, and I will meet you in the next session. And again, please do check the Prepaze website to book a free trial class. All right. So hope you like this session now. Okay, then see you then in the next session. Bye.